So in the last video, we talk about what is the distribution of the sample mean, or what is the sampling distribution of mean. So to find out the sampling distribution of the mean, what we do is we pick many samples of the same size, meaning you pick one sample of size 30, another sample of size 30, another sample of size 30, and you continue doing that. And you find out the mean or the average of each of those samples. And if you make a table and then write what is the mean and then how many times that mean is repeated, that is like X bar and the frequency, 2 columns, right? And if you complete that table, and if you draw the histogram for that distribution table, then you will get approximately normal distribution. That table is called sampling distribution of mean or distribution of sample mean. And the histogram shows you that the distribution or the graph was almost normal, almost bell-shaped, right? So now we will discuss here when does that graph is bell-shaped and when does the graph is not bell-shaped. We will discuss that here, okay? Also, we will do some applied problems and then we will state the central limit theorem, which is very famous theorem. And then we will apply the central limit theorem to do some of the problems there. Okay, let us go over this. In addition to knowing how individual data values vary about the mean or for a population, statisticians are interested in knowing how the means of sample of the same size taken from the same population vary about the population mean. Okay, a sampling distribution of sample means is a distribution obtained by using the means computed from random samples of specific size taken from a population. Sampling error is the difference between the sample measures and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. What does that mean? That means because you see that in the last example, in the last video, we found the mean of the sample means, that was 70.9. But the population mean was 71. You see that 0.1 years different? That is basically the error. Meaning when you find out the sample is a small size, right? When you find out the sample and find the mean of those samples, then that may be a little bit different from the population mean. So that is because the sample you took, it is not representing, may not be representing all the population. Okay, that is the error. That is a chance of error. That is called the sampling error. Okay, so the population, the properties of the distribution of sample mean, the mean of a sample means will be the same as the population mean. We saw that, right? And the standard deviation of the sample mean will be smaller than the standard deviation of the population, okay, and will be equal to the population standard deviation divided by the square root of the sample size. That is, we got sigma over root n, right? That will be the n is the sample size, sigma is the population standard deviation. So the sample standard deviation will be smaller than the population standard deviation. What does that mean? Sample standard deviation. That means sample standard deviation of the sample mean, that's how we said, is smaller than the population standard deviation. But how much would that be? Is sigma over root n, to be specific. Okay, let us state the central limit theorem. As sample size n increases without limit, the shape of the distribution of sample means taken with replacement from a population with mean mu and standard deviation sigma. A population has mean mu and standard deviation sigma. If you pick many samples with bigger and bigger sample size, then the distribution of the sample mean will be approximately normally distributed. That's what it is saying. Approach to a normal distribution. As previously mentioned, this distribution will have a mean mu and a standard deviation will be sigma over root n. So what does that mean actually? So the distribution of x bar will be normal with mean will be mu x bar. And the standard deviation will be s x bar. But what is the value of mu x bar? Mu x bar will be same as mu. Sigma x bar will be same as sigma over root n. That's what it is saying. Okay. So what we do now is we want to use the central limit theorem to do some problems. But before that, let us do example 1. A normally distributed population has mean 29. What does that mean? That means mu is equals to 29. and standard deviation is 3.2. Sigma equals to 3.2. Now, if a sample of size 43 is selected, so n is equals to 43 is selected, find the mean and standard deviation of the distribution of x bar. For x bar, the mean is denoted by mu x bar. How much would that be? That will be same as 29, right? Because what we said is that for the sampling distribution of the sample mean, the mean of the sampling distribution is same as the population mean. But how about the standard deviation of the sampling distribution? It will be sigma over root n, right? How much would that be? Sigma is 3.2, right? And then root over 43. That's what you get. And if you use calculator, you will get 0.488. Let me write down that. You will get 0.488. Did you see that? The standard deviation of the sample means is smaller than the standard deviation of the population. But the mean of the sample means is equals to the mean of the population. That's what it is saying. Now, let us read these two notes. When the original variable is normally distributed, if the population is normally distributed, then the distribution of the sample mean will be normally distributed for any sample size n. Okay. If the original population is normally distributed, then the sample size does not matter. Any sample size, the distribution will be normally distributed. But when the distribution of the original variable is not normal, if the original data is, the population data is not normally distributed, a sample size of 30 or more is needed. That's it, the bigger sample size is needed to use the normal distribution to approximate the distribution of the sample mean. Meaning, if the population data is not normally distributed, then the sampling distribution of the sample mean will be approximately normal if sample size is bigger than 30. Otherwise, it may not be normal. The larger the sample size, the better the approximation will be. That's what he's saying. The central limit theorem can be used to find the probability of something when a sample size n is chosen in the same manner that it is used to answer questions when the individual value is chosen. So we use exactly the same technique to find out the probability. Only the difference will be, instead of x, it will be asked x bar. Okay. Now again, there are two different methods. One is the g-value method, the other is the direct method. Previously, we had g equals to x minus mu over sigma. But now we will have g equals to x bar because the question will ask about x bar. X bar minus mu over sigma over root n. Instead of sigma, we will have sigma over root n now. Okay. So I will show you both method, but let us do this. You can do the problem directly without changing to the g. So you can use like directly that we did previously, or you can use g value method and then do after finding the g value. Okay, let us see that. Consider a normal population. Mu is 34.9 and sigma is 4.1. Now, if a sample size n is 36, it's chosen, find directly using calculator probability that x bar is greater than 33. Let us do that. Let me draw the graph. This is the normal distribution. What is the mean? Is 34.9. Mean is different from 0. It is not g. It is normal distribution, right? Normal distribution because the sample size is bigger than 36. It says sigma is 4.1. So x greater than 33 will be, x is somewhere here. So greater than 33 will be the right side of that, right? So the right side of that. So basically you are trying to find out that area. So how do you do that? Is you do normal CDF, right? What is the left bound here? Left bound is 33, right? 33. So 33. The right bound is it keeps going. So it is 10 to the 10, right? What is mu? Mu is 34.9. But instead of sigma, what we put is we put sigma over root n. That is the standard deviation of x bar, right? Because what we know is x bar is normally distributed with mean mu and standard deviation is sigma over root n. Okay. Since if it was x, then there will be no root n because n will be 1 in that case. If you pick only 1, then there will be just x. Then there will be sigma over 1, that is just sigma. But if there is x bar has the sample size, In that case, you will have to divide sigma by 4.1 divided by what is n is 36, and let us use calculator for that. Okay, so what I'm going to do is I'm going to use normal CDF. Let me do that. Let me clear this, and I want to choose a TI-84 calculator, TI-84 plus only. Okay, so what you do, second verse, and go to the normal CDF because you are finding the probability. That's why you use normal CDF. Okay, normal CDF, and then what is the lower limit is 33. 33 is the lower limit. Upper limit is 10 to the 10, right? 10 to the 10, and mean is 34.9. Is that what we have? Yes, 34.9. So that will be 34.9, and then the sigma is basically sigma over root n. So sigma is what was sigma? Sigma was 4.1, right? 4.1 divided by root n, that will be second, and then where is root? Second and x square will give you root, and then 36. That's what you will get. Okay, now if you hit enter there, that is the thing, you will get 0.9972. 0.9972. That is about 99% chance. 0.9972. If a population has mean 34.9 and sigma 4.1, if you pick a sample of size 36, then the probability that the average of that sample is greater than 33 is 99.72. That is the chance of happening that the sample's average is greater than 33 is 99.72%. So you can describe that way. Okay, let us do another example. Less than 37. So exactly the similar way, right? So the mean is 34.9. So 37 will be somewhere here, right? So you are trying to find out the area left of that because it says less than. So how do you do that? Is normal CDF. Left bound will be negative 10 to the 10, right? Because it keeps going on the left. Right bound is 37 because that value is 37, right? And mean is 34.9. Sigma is 4.1 over root under 36. I forgot the root there. Okay, you close that, and if you use calculator for that, you will get, let me do that. So let me clear what I have. Second verse normal CDF. I hit enter. The left bound is negative 10 to the 10. You can write that way, and then the right bound is 37, right? On that the shaded region, and mean is 34.9. Sigma is sigma over root n. Okay, and hit enter. You get 99.89. It is even bigger. So 0.9989. In terms of the percentage, it is 99.89%, right? The previous one is 99.72%. So what does that mean? That means there is a 99.89, almost 100% chance that the average of that 36 sample size will be less than 37. The reason is because the population mean is 34.9. Now, for the last one, you will have to do, so the middle one is, let me use different color. So the middle one there is 34.9. It is asking 32 and then 36. You want to find out the area between that. What is the normal CDF thing? Normal CDF. Left bound is 32, right bound is 36. So 32 comma 36 comma 34.9 comma 34.9 comma 4.1 over root under 36. If you do that, then use calculator for that. Okay, if you use calculator, what do you get? Let me clear that. Go to second verse normal CDF, hit enter. The lower bound here is 32, right? So 32 is the lower bound. The upper bound is 36. 36. Mean is 34.9. The standard deviation is sigma over root n because we are talking about x bar average. Okay, that's why. And hit enter. You get double enter. 94.62. 94.62%, or you can write 0.9462. What does that mean? That means there is a 94.62% chance that the average of those 36 sample will be between 32 and 36. That's what it is saying. Okay, now if you want to do by the g-value method, how do you do that? Is you first find out g for this 33 using that formula. Okay, so what will be the g? G will be 33 minus mu is 34.9 divided by sigma over root 10, 4.1 over root under 36. Okay, this is what you do, and then use calculator for that. You will get, then you will get, this is negative 1.9 divided by 4.1 over 6, because the root under 36 is 6, right? If you use calculator for this, you will get negative 2.7805. That's what you get. Okay, now what you want to do for the first problem is probability that x bar is greater than 33, which is equals to probability that g is greater than negative 2.7805. So how do that look like? It will look like, because this is g distribution now, I'm using the g-value method. Okay, there is 0 and then negative 2.78 will be somewhere here, negative 2.78, and you are trying to find out the area right of that, right? What do? Normal CDF, left bound is negative 2.78, right bound is 10 to the 10, and then 0, 1, because this is converted to the g value. Okay, and if you do that, you will get exactly the same answer there. Okay, so similarly you will do the second one. For the third one, you need to find out the g value for 32 and g value for 38, and then you use the g value and the calculator. Okay, let us do some examples. Okay guys, so let us do that. AC Nielsen reported that children between age 2 and 5 watch an average of 25 hours of television per week. What is that? The mu is given. Mu is 25. Mu equals to 25. Okay. Assume the variable is normally distributed. See, the variable, the data is normally distributed. It is given. And the standard deviation is 3 hours. Sigma is 3 hours. Okay. If 20 children between n equals to 20, between age 2 and 5 are randomly selected, find the probability that the mean of the number of hours. See, mean of the number. What is asking is probability that x bar of hours they watch television will be greater than x bar. The mean is greater than 26.3 equals to what? That's what it is asking. The probability that x bar is greater than, probability that the average of those 20 children is greater than 26.3 hours is what? That's what it is asking. Okay, now see, I'm using both methods. The direct method will be p x bar greater than 26.3 is equals to normal CDF 26.3. This is the graph, right? And then right area means 10 to the 10, and then 25 is mean. So left bound, right, mean, and then sigma over root n, because we are talking about the x bar. That's why you do that directly. Okay, but if you want to do the g value method, first we'll find out g by x bar minus mu over sigma over root n. What is x bar? X bar is whatever we have. That is the x bar value we use. 26.3. Okay, and then minus mu is how much is mu? 25 over 3 over root under 20. If you simplify that, you will get 1.94. That's what you will get. Okay, now probability x bar greater or equals to 26.3 is equals to probability of g greater than 1.94. Okay, so here is the thing. Sometimes there you will see just greater than, and sometimes you will see greater or equals to. It does not matter. So for both you will get the same answer. Okay, so 1.94, that will be given by either you use here normal CDF, left bound is 1.94, right? Right bound is 10 to the 10, you can say, and then 0 and then 1, because I'm using the g-value method here. If you want to use direct method, you can just use calculator for that. Let us find out those values. Okay, so either way you'll get the same answer. So second verse normal CDF, because you are finding the probability. So the lower bound is 26.3 3, right? And the upper bound is 10 to the 10. I'm using the direct method first. 10 to the 10, okay? And then mean, what is the mean? Mean is 25. And then the sigma will be sigma over root n, right? So it will be 3 over root, that is second, and then square. Root n is 20. And then close that. This is what you get. So hit enter. This is what you get. And if you find the probability, you will get the probability is basically, let me see, 26.3, and then 10 to the 10, 25. Did I do that right? Instead of 25, I wrote 35 there. It should be 25, okay? So let me go down and then write 25. 25, okay? Now you will see the probability is 0.0263. That's what you will get. That will be 0.0263. Or if you use this way, you will get the same answer, 0.0263, okay? So previously I was putting the wrong number there. Instead of 25, I put 35, okay? So let's do for the g-value method. In the g-value method, you see, so the left bound is 1.94, right? 1.94, that is the g-value we got. The right is, that is good. And then the mean is 0, sigma is 1. So you can do that and then hit enter. So you will get 0.0262. So here you get 0.0263, but here you get 0.0262. Why is that? Because of the number of decimal you consider there, okay? So on here, when I found 1.94, I consider only, see, when I find that 1.94 here, then I consider only 2 or 3 decimal places when I use that. So I am missing some of the decimal numbers there. That's why I was doing 1.94. It may be 1.933 something, or 945 like that, okay? 4436 like that. That's why, because of the decimal, you get something slightly different, but they are the same thing. All right. So instead of selecting a sample size 20, if we select a kid with age between 2 and 5, what is the probability that he watches more than 26.3 per week? Look at that. Here you are selecting a sample of size 20. Here you are selecting a sample of one kid, only one kid. If there were more people selected, then you will have to use average, because it says what is the probability that the mean of those. But here it is not asking what is the probability that he watches more than 26.3. What it is asking is probability of x greater than, not x bar, just x. If you are selecting 1, you do just x. If you are selecting more than 1, you do x bar there, okay? So if you use that in your calculator, so you don't need sigma over root n. If you are selecting more than 1 and if you are taking the x bar, then you need sigma over root n. But if you are selecting 1, you can do sigma over root 1, right? Because n is 1 here. That is just 3 over root 1 is just 3, right? So let us talk about that in the calculator. So what I'm going to do there is second verse, instead of doing 20 people, I am doing, so there is, let me do 26.3, right? The right is 10 to the 10. Mu is 25, sigma over root n, because n is 1, so sigma over root n is just sigma, right? Sigma is just 3. Instead of 3 over 20, you have just 3. So what is the probability you get? Instead of selecting the mean, the 20 people and finding the mean probability for the mean, we are doing just one person. So it is 0.33. What was that? 33 and then 24. That's what you get. So when you select 1, then you will have n equals to 1 there, and then it is just writing, it is just like 6.2 in that case. Okay, so let us do a couple more examples and then we will be done. All right, so let us do this. Example number 5. The average age of the vehicle registered in the United States is 8 years or 96 months. Since all other things are given in the months, okay, then we will write month. So mu equals to 96 month. What is the standard deviation? Is sigma is 16, right? A random sample of 36 vehicle, n equals to 36 is selected. Find the probability that mean of their age is between 90 and 100. What is it asking? Probability that 90 is less than x bar, mean. That's why x bar is less than 100. So what do? Normal CDF. Left bound will be, because if you draw the graph, it will look like the mean is 96. And it's saying, asking between 90 and 100, right? Between 90 and 100. This is what it is asking. So 90, 100. So the left bound for the shaded region is 90. Right bound is 100. What is mean? Mean is 96. Now we need sigma over root n because of the x bar. Sigma is 16 over root under 36. Now use calculator. What do you get? You will get, so let me do that. Second verse, normal CDF. Okay, normal CDF. The lower is 90. The upper is 100. And then a mu is 96, the mean. And then sigma is sigma over root n, right? Sigma over root n is 16 divided by square root of 36. That's what you get. Close the parenthesis and then go down and then hit enter. This is what you get. 0.92093 you can say 921 0.921. That's it. You can do by g value method. If you want to do the g value method, then you need to find out g first, right? G equals to x bar minus mu over sigma over root n. Find out g and then use the technique we use in the 6.1. Example number 6. Let's do example 6. The average cholesterol content of a certain brand of egg is 215. So mu, population mean, is 215 and the standard deviation is 15. Assume that the population is normally distributed. All these problems needs either normally distributed or the sample size greater than 30. If a sample of 35, n equals to 35 are selected, find the probability that the mean, that is probability of x bar, will be larger than x bar is greater than 220. So how do you do that? Let me use different color. So, right, the mean is 215. The question is asking greater than 220. That's what it is asking. So how do you do that? Normal CDF, and then left bound is, this is 220, right? This is 220. So 220 and then 10 to the 10 and then mu is 215. Sigma is sigma over root n because of the x bar. Okay, sigma over root n, root under 35. Use calculator there. Okay, find the probability that the mean of the sample will be between 210 and 225. What it is asking? Probability that x bar mean is less than greater than 210 and less than 225. So it will be normal CDF in the calculator. It will be 210 because what is happening there is basically there is a normal distribution. Mean is 215 between 210 and 225. That's what you are trying to find out, that area. 210, 225, right? 210, 225. Mean is 215. Sigma is sigma over root n. The standard deviation is the sigma over root n. Okay, so what do you get? You use the calculator for that. Now, if only one egg, if there are more than one, then you need x bar. But if only one egg is selected, what it is asking is probability that x is greater than 220. That's what it is asking. See, if only one egg is selected, find the probability that the cholesterol content will be greater than 220. That's what it is asking. So again, it is, the figure will be the same, right? 215 is the mean, and then you will just find out that 220. But in the normal CDF, the left bound is 220, right bound is 10 to the 10, right? And the mean is 215. Sigma is just sigma. You don't have to divide by root n because n is 1. Okay, sigma is 15 over root 1, that is just 15. So you can do that. So you don't have to even write root 1 because it is not asking mean. If it was asking the mean, then you would need root n, but otherwise you don't. And then you use calculator to find out that. Okay, let us do the first one in calculator. How does that look like? Okay, on the first one, so what you do is, let me clear what I have. Second verse, normal CDF, and the lower bound for the first one. Let me go to the figure. It will be easier to see the figure. On the first one, the lower bound of the shaded region is 220. So 220. And the upper bound is 10 to the 10, right? 10 to the 10. And then mean is 215, 215. And then sigma will be sigma over root n. That will be 15, okay, divide by root n is 35, right? So let me do that, 35. So sigma over root n. And go to the paste. If you hit enter, you will get 0.0243. That is the answer for the first one, 0.0243. How about the second one? For the second one, you have the left bound is 210, 225, right bound, right? So what you will do is second verse and the normal CDF, you do 210, and then the second one is 225. The upper bound is 225. So everything other thing are same. Mean and sigma over root n, they are the same thing. And if you get that, you will get 9757, 0.9757, 0.9757. Okay, for the last one, what would you do for the last one is, let me go there. You know what, if only one thing is changed, what you can do is you can do second and then enter. That will copy that thing, okay? Or you can even do second and then enter again, will give you the previous one, okay? So it will give you the previous one. Okay, look at that. All those previous one you can get, okay? If you want to do that like faster way, then you can do that way too. Okay, let us do the last one that has second verse and then normal CDF. And then it says 220. Let me do 220. And then by the way, the first one is the left bound is 220, right? 20. The right bound is, it is infinity, this 10 to the 10. And then the mean is 215. The standard deviation is just 15, right? 15 over root n will be just 15. And then if you paste that, you will get 0.3694. So 0.3694. That is a higher chance that if you select one person, then there is a higher chance that you will get the cholesterol content in one egg is greater than 220 than the mean. Okay, to be mean greater than 220, most of the data you pick from that sample needs to be bigger, right? But which is lower probability because the mean is 215. But one or two data can happen that way, so that may have higher chance. So all these, example 7, example 8, all these are done exactly the same way. Okay, guys. So we are skipping 6.4 because 6.4 is the binomial theorem, binomial problem. Okay, you can use the technique we learned in the previous chapter. Okay.